So here, let's start Calculus 2 by reviewing integrals to the extent that we learned them in Calc 1. These first few class periods, and then we'll get into new ideas about integrals, more depth on doing them, more approximation methods, more applications for these next couple months. We go through chapters 7 and 8. And it's easiest, I think, to always think about integrals in terms of motion. I think it's the easiest kind of application to think about, easy to visualize, though next week we do want to talk about other applications as well. And with integrals, what you're typically going to be given is not the position of an object, but its velocity. The velocity of an object, like a car, or a bug, or a ball, or more generally, what people typically call it is a particle. Velocity of a quote-unquote particle, though that has connotations from chemistry, like, okay, is this an atom? Is it an electron? Well, it could be, though mostly I will be thinking about like people walking or cars moving or balls going up and down in the air. But I can still call it a particle. We don't have to imagine the motion as being up and down. We could imagine as being left and right. If the motion's up and down, it makes intuitive sense to think of the upward direction as the positive direction and the downward direction as negative. Makes sense. But that's not unique. You could switch it around. You could make downward positive and upward negative. I won't, but you could. For left-right motion, bias toward right-handers, I guess, you think of the rightward direction, like on the number line, as being the positive direction, and the leftward direction as being the negative direction. When the velocity is, so we'll think about left-right motion today. When the velocity is positive, then, that means the object, the particle, is moving to the right. That's positive velocity. When the velocity is negative, that means it's moving to the left. When it's zero, it means it's either sitting still or maybe at an instant in time, it's turning around. Or even, this is even more subtle, it stops for an instant and then continues in the same direction. That can happen too. At least from a modeling perspective, you can model it that way. So we got the velocity of a particle given by some function, v equals f of t. Of course, you want to use units if you're going to apply it to real life. And the units you choose depend on the situation. I mean, if you're talking about a molecule or an atom moving around kind of slowly, I mean, if it's in the air, it's moving around fast, actually, right? If it's a gas, the atoms move fast. But I don't know, if it's in a solid, if it's in your breakfast, it's moving around kind of slowly. Maybe it's appropriate to use like millimeters per minute. I don't know. Centimeters per second. Okay, well, I'm going to use meters per second for my velocity. Use the standard units. M per S means meters per second. Meaning time is in seconds. That would be my units. In a calculus class, you typically write these things with some formula, hopefully some simple formula like, oh, I'm going to pick 4t minus 4t squared. Why did I pick that function? It has some nice properties. If you factor it like this, you can see one nice property is it's got simple t-intercepts at 0 and 1. When t is 0 or 1, that's where the graph's going to touch the horizontal axis. It also happens to be the case that the maximum value of this function is 1 when t is a half. The graph looks like this. I will graph it. It's got a maximum value of t equals a half. So that's another nice property. A maximum value of 1 meter per second, in this case, when t is 1/2 second. But again, the motion is along some number line, say going left and right, with, say, the positive direction being to the right, the plus x direction in meters is what that is giving us. Where is the origin on the number line? You would want to decide. I'm not going to write where it is at the moment. I will later. Okay. You typically would want to pick the origin to be where the location of the particle is at time zero. Typically, right? Because it's simplest. That's a modeling principle. Try to be as simple as possible. But it could be the case that it's starting somewhere besides the origin at some other time besides time zero. That could be the case. Be a little weird, but it could be the case. Another little subtlety here is you might wonder, when would a particle ever have this velocity exactly? Right? Would that ever happen? Probably not. Right? This is a very precise mathematical function, giving you precise values of velocities at precise moments in time. But from a measurement perspective, right, we got some uncertainty in our measurements. Usually numbers don't come out so precise. Probably there's no particle that ever traveled with this velocity exactly in the history of the universe. But maybe it's a good approximation. People do use polynomials like this as good approximations, for example, with free fall. Is this a free fall situation? No. Okay, I'm imagining it to be a left-right motion. The velocity is a derivative. It's the derivative of x with respect to t. I'm using x as my position variable. That's arbitrary. I could have used y. Since I'm imagining it to be left-right motion, it makes more intuitive sense to use an x. If it's up-down motion, I'd be more likely to use a y, right? X-axis horizontal, y-axis vertical. Let's graph this function to get a feel for what its motion is like. How is the particle moving? Let's graph the velocity as a function of time. This is a parabola, right? Quadratic. Downward opening because the coefficient of t squared is negative. So it's that kind of shape. T-intercepts 0 and 1. Let's say that's 1 right there. And the maximum value, I said, of 1 when t is 0.5. So the graph looks about like this. In theory, this could be valid even when t is negative. The particle could be moving before you set time equal to 0. Using the stopwatch on your phone or your watch. It could be at position 0, say at time 0. And so therefore it could be moving before time 0. But it doesn't have to be. We could be thinking about applying this only when t is greater than or equal to 0. We can find its values. For example, f of 1/2, f of 0.5. Let's just confirm that we get 1. I'll plug in a half. You should feel comfortable with fractions in this class. I'll plug it into this formula here. 4 minus times a half minus 4 times 1/2 squared is 2 minus 4 times 1/4. 2 minus 1 is 1. Don't forget your units, meters per second. So is that an average velocity or an instantaneous velocity? What do you think? You want to say, Daniel? It's instantaneous. This is the velocity function giving you the exact instantaneous velocity at any moment in time. It's a derivative of the position. It is an instantaneous velocity. At that moment in time, t equals 0.5, the velocity is 1 meter per second. That's how fast it's going to the right. Now, the idea of instantaneous velocity is a bit confusing. We tried to dispel that a bit in Calc 1, right? That was a big thing in Calc 1. It's a limit of average velocities. Here we're kind of assuming you're comfortable with that. F of 1 for example, is 4 minus 4 is 0 meters per second. F of 2, for example, is 8 minus 2 squared is 4 times 4 is 16. Negative 8 meters per second. At time 2, the particle is moving to the left at a speed of positive 8 meters per second. Speed and velocity are not the same thing, but they're related. Speed is the absolute value of the velocity. When I say the velocity is negative 8 meters per second, I'm saying the speed is 8 meters per second, but the motion is to the left in the negative direction. So what is the motion here? What's going on? How can I imagine this? At t equals 0, at that moment in time, the velocity is 0. The object, the particle, is not moving. But even for ever so slightly positive values of t, the velocity is positive, so the object is moving to the right. Does that mean it has to speed up? Yes, it is. The acceleration is the derivative of the velocity. It's positive. It's the slope of this graph. It's positive right here. It's accelerating. It's moving as it moves to the right. Accelerating until it gets to 0.5, where the velocity is maximized. That 1 meter per second is as fast as the particle is going to the right. As this graph goes down, as it decreases, it's still a positive velocity, so it's still moving to the right, but it's slowing down because the velocity is going towards 0. At time 1, that's the turnaround moment. At that instant in time, the velocity is 0. What's going on? The particle is turning around, going like this and then turning around. At that moment in time where it reached its most far right position, that's the moment in time where it turns around and starts going in the negative direction. The velocity is negative. And in fact, it's becoming more and more negative, meaning it's going faster and faster as it moves to the left. The speed is increasing. You might say it's accelerating, though, careful, the acceleration itself is negative because you're going faster and faster in the negative direction. Let's find the acceleration here. Let's go ahead and take the derivative. The second derivative of the position in Leibniz notation is written like that, is the same as the first derivative of the velocity. Excuse me. The velocity is the function f of t. I could use prime notation as well. That's f prime of t. No need for a limit here. You don't have to go back to the limit definition of the derivative in this class. Will you ever have to again in any class? I can't rule it out, but it won't typically happen. You can just take the derivative as you know how here. The derivative of 4t is 4. Carry the minus sign along. The derivative of 4t squared is 8t. So there is the acceleration. You could call this a. Its units are meters per second, because it's a rate of change of velocity with respect to time. At any moment in time, like t equals a half, you get the acceleration at that moment in time. And yeah, it's a little difficult to understand what it means. Meters per second, shorthand meters per second squared, but that is just a shorthand. Meters per second squared, if you've never understood this, it's a shorthand. It really means meters per second. At time 1, for example, your acceleration is -4 meters per second, meaning at that moment in time, you're going in the negative direction, you're actually speeding up at a rate of 4 meters per second every second if you kept speeding up at that same rate. Going faster and faster. Kind of hard to understand. It is the slope of the velocity graph. Zero slope there, slope of -4 here, slope of -8 down here somewhere. F prime of 0 is positive. Positive 4 meters per second squared. Positive slope here. It can be informative to graph the acceleration as a function of time. It's a linear function of time, not constant. It's not like free fall. Free fall under gravity, no air resistance, so you're in a vacuum chamber. Free fall under gravity is a constant acceleration, 9.8 meters per second downward. This acceleration is not constant. It's a function of t. It's changing over time. Going from 4 to -4 as t goes from 0 to 1. Starting out with a positive acceleration. It's telling you the slope of this graph. Positive acceleration as you're moving to the right. So you're not only speeding up. Well, okay, you're speeding up, though you are speeding up slower and slower, you might say. The velocity is increasing, though the rate of increasing is decreasing. The graph is concave down. The derivative of the acceleration is negative. Does anybody know what the derivative of the acceleration is called? Oh, this is something funny that I didn't talk about in the first class. It's called the jerk. The derivative of acceleration, the rate of change of acceleration, is the jerk. Jerk your neck. In this example, it's negative and it's constant because this slope of this is negative and constant, reflecting the fact that the velocity graph's concave down. First derivative is velocity. Okay, x's position, its derivative is velocity. Its second derivative is acceleration. Its third derivative is the jerk. I think maybe I mentioned in Calc 1, what's the fourth, fifth, and sixth derivatives? Rice Krispies. Snap, crackle, and pop. Seriously. Scientists have to have fun in some ways, right? That's seriously what they call the fourth, fifth, and sixth derivatives. Snap, crackle, and pop. You can look it up. You don't want a high pop. Break your neck. Okay. Anyway, that's some information about how to think about this with velocities and accelerations. But we want to go back with integrals to position. And we want to answer questions like, what is the position of the particle at various times? Oh, say like t equals 0.5, 1, 1.5, and 2 maybe. Now, technically speaking, the way this problem is phrased, the answer depends not just on the velocity, but also where you start. Are you really starting at position 0, the origin, at time 0, or not? Because if you're not, you have to adjust for wherever you're starting at time 0. To keep things simple, let's assume it starts at position 0, at position x equals 0, just to keep things simple. We could assume other positions, just to make things more complicated. Is there a purpose for making it more complicated? There is, if it's to make a conceptual point. The conceptual point being you can do it if you want. But a modeling principle is keep things as simple as you can. So how do you do that? You know, you learned this in Calc 1, right? How do you figure out the position? Integration. Could we just find an antiderivative of this? Yeah, we could, but let's write it in terms of a definite integral first. the change in position is given by integrating the velocity. Notice I'm saying change in position, not position itself. Also called displacement. To find the change in position, you want to integrate the velocity. Say it again. Very important application. To find the change in position, when you know the velocity, you integrate the velocity. Over what time interval? That's up to you. Let's do it from t equals 0 to t equals 0.5 to start. The velocity function is 4t minus 4t squared. That's my v equals f of t. When you show your work by hand, you don't have to write what I just did there. I'm just doing it for clarification. That's what this function is. It is the velocity. And I integrate over the interval. Which, of course, means, I hope you remember, you could do that by estimating the area under the curve. And we will do that, including today for a harder example. But there's an easier way to go that's more precise. What's that easier way to go? It's a theorem. It's got a name. Fundamental theorem of calculus. FTC. Fundamental theorem of calculus says to do a definite integral like this, find an antiderivative or antiderivative if you prefer. I never know what's going to come out of my mouth, anti or anti. Integral of 4t is 2t squared, right? Check by differentiation. Derivative of 2t squared is 4t. Integral, this one's a little trickier, of 4t squared is going to be 4/3 t cubed. Check by differentiation. I am, of course, using a general fact there. When I do that, actually a couple general facts. I'm using the fact that the integral, say, of x to the n power is x to the n plus 1 over n plus 1 plus c. Don't forget to write a plus c when you write an indefinite integral with no limits of integration. The plus c must be there, including on the gateway, which means since the gateway is always indefinite integrals, every single answer has a plus c. Don't ever forget it. They put the plus c right there at the beginning. Okay. Why do we make you do it? In fact, Mathematica doesn't bother putting a plus c. Mathematica would fail the gateway. It's because we want to emphasize it's important. Why is it important? Differential equations is one example where it's important. Having the plus c there is important to find what's called a general solution, which then helps you solve any initial value problem in a differential equations problem, which we will be doing in chapter 11 in this course. Actually, this equation is not always true. When is it not true? We do not want n to equal what? Don't want to divide by 0, right? N better not equal -1. Well, what do you do when n does equal -1? Well, there you're integrating really 1 over x, because that's what x to the -1 power means. What's the answer there? Natural log. Log natural in French, except I'm not pronouncing it as a Frenchman. of x? Yeah, plus c. However, this function is defined for negative values of x as well, and natural log of x is not defined when x is negative, at least in this class. Well, actually, natural log of a negative number is defined. In Mathematica, log actually means natural log. It's just that it's an imaginary number. Log of -1 is I times pi. I is the imaginary unit. I squared equals -1. E to the I times pi power. I can do that. Plus 1 is 0. Wait, oh, that's e to the I. E to the I power plus 1 is 0. What in the world am I talking about? You may have heard of e to the I pi plus 1 power equaling 0 before. It's the most famous equation in math. Anyway, that's related to this. We're not going to get into that right now. That's just for fun. So for us, we want absolute value signs there to get a more general antiderivative. It's actually not quite as general as it could be, because the plus c when x is positive could be different than the plus c when x is negative. Oh, that's a bit too much to worry about. Anyway, coming back to this, we're also using the fact that the 4s and the minus signs can get carried along for the ride. That's called linearity. Let me not get into that. We need to evaluate this from 0 to 0.5, meaning this notation means plug in the top number and then subtract what you get when you plug in the bottom number, although that's going to be a couple zeros. For you guys, I'm doing decimals. For the first class, I actually did fractions here. Fun. 0.5 squared, 0.25. That's supposed to be a 0.5 here, sorry. 0.5 cubed is 0.125. That's a 0.5. That ends up being a 1/8. 4/3 times 1/8. The 4 and the 8 cancel to give a 1/2. It's 1/6. 0.5 minus 0.16 repeating it. As a decimal, it's 0.3 repeating, or 1/3. Units would be meters. Okay, I did that all with decimals mostly. No, I guess there's some fractions in there. I mixed up my decimals and fractions. You should feel comfortable doing either way. Work on your fractions if you need to work on fractions. It's good for you. It's like eating vegetables. Work on your fractions. If you feel afraid of fractions, you're not alone. Plenty of people, even in calculus, feel afraid of fractions. Okay? It's like just you never got over it since 4th grade. Work on it. Okay? If your fraction manipulation is rusty. Very precise kind of answer right there. 0.3 or repeating, infinite precision. Again, in real life, there'd never really be a particle that would travel with this exact velocity. And so you'd never get an answer that precise. In math, yes, it comes out that precise, but in real life, you're always doing approximations. There are plenty of problems I give you where I ask you to give answers both in exact form and approximate form to so many decimal places. Okay, we can do that here. I don't typically worry too much about significant figures in this class. Maybe never. But of course, significant figures are very, very important in science. So you should, in science classes, pay attention to significant figures. In my classes, I don't really care about significant figures because in part because I'm not a scientist, but in part because I just find it too boring. So I don't know, I just say round to so many places after the decimal. Yes, pay attention to them in your science classes. It's important. All right. So now should I keep going? Should I find the change in position to time 1, time 1.5, time 2? Yes, but I'd like to be more efficient about it. How can I be more efficient about it? I'll show you. before I do that, I should remark that this is giving us the change in position, not the position itself. The change in position is only the same as position if you start at position 0. Then if your change in position, for example, is -2, that means maybe you went to the right before going to the left and you ended up 2 meters to the left of where you started. That's the change in position. It's the same as your position -2, if you start at position 0. But if you start at position 5 and your change in position is -2, you'd end at position 3. 5 plus -2 is 3. But we started at position 0. Therefore, I can say position at time equals 0.5 is 0 plus 1/3 meter. It's the same answer, emphasizing to add 0 because that's the starting position. But if we had some other starting position, then we need to put that other starting position there before adding on the value of the integral. How can I be more efficient in finding change in position in general? Change in position from time t equals 0 to some arbitrary time? What should I call the arbitrary time? Just plain little t? I could. Maybe though, since my function, my velocity is already a function of little t, maybe I should use a different letter. But it's still going to represent time. Oh, how about capital T? It's a little weird. Bear with me here. So I'm going to integrate the velocity 4t minus 4t squared from 0 to capital T. It's as if the upper limit of the integral is a variable. Is it a variable? Yeah, you could call it a variable. Why? Because it's a letter that represents a number that could take on different values. That's why. Is it different than little t? Well, they both represent time. When I do the integral, maybe I want to think of capital T as fixed and little t as a variable, but then maybe at the end, I want to think of capital T as a variable. Is that okay? Is that allowed? Sure. Whether something is a constant or a variable is all in your head. I say that a lot. People from Calc 1 know. Whether a letter represents constant variables, all in your imagination. Completely serious when I say that. It's all in how you conceptualize it. Do this integral just like before. Antiderivative is 2t squared minus 4/3 t cubed. Evaluate from 0 to capital T. Plug in capital T. Subtract what you get when you plug in the bottom number, which is going to be a 0, but I'll write it there anyway. This simplifies to 2 times capital T squared minus 4/3 times capital T cubed. It's a function of capital T. Should I call it little f of capital T? No, don't call it little f. Why not? Because we already have a meaning for little f. It's the velocity. Call it something else. Got an idea, Daniel? Oh, good. Where's the plus c? I'm doing a definite integral, so I don't need it. If I put a plus c here, which I could do, when I subtract, it would cancel because it would be in both spots. Call it something else. How about capital F? Oh, that should ring off alarm bells in your head. Capital F of t, and this is the position, this is x. At time capital T. But then I look at this and I say, well, why did I even bother with a capital T? I like little t better. Let me write little x equals capital F of little t equals 2 times little t squared minus 4/3 times little t cubed. I kept the f a capital, but I changed the t to a lowercase. What in the world am I doing? It is the same function, so I better use a capital F still. But I prefer using little t as a variable, so I changed the capital T to a lowercase t, just because I felt like it. Did I have to do that? No, but I felt like it. A function is not determined by the name of the function or the name of the variables. It's determined by how the inputs affect the outputs. It's the same formula. For emphasis, I like doing something like this. This is a side comment. The function g of x equals x squared, and the function h of O treble clef equals treble clef squared are the exact same functions. Yes, I'm treating treble clef as a variable. I like making treble clef symbols. They're pretty. Why are these the exact same function? Because for any given input, they give you the same output. That's why. If the input is 7, they give you an output of 7 squared, 49. If the input's -4, they give the same output, 16. It doesn't matter that the function name is different. It doesn't matter that the variable name is different. They are the same function. Same kind of idea here. And now this function can help us find change in position and ultimately position at other times, including, for example, time 1, 1.52. For the sake of speed, let's just do it at one more time. The position at time 2 would be 2 times 2 squared minus 4/3 times 2 cubed. That'll be 8 minus 32 over 3, I think. Double check that in my head. 8 is 24/3. Got a common denominator there. We get -8/3 meters, -2.67 approximately meters is the position at time 2. You are to the left of where you started. This area gives you the change in position from time 0 to time 1. If I subtract an area over here, that'll give me my integral from 0 to 2, my change in position from time 0 to time 2. And it's negative. And it's the same as the ending position because the starting position, again, is 0. To end class today, got 7 more minutes, we want to focus on something weird that can happen. Not just for the sake of weirdness, but for the sake of realizing this is important. And no, we will not do any more imaginary numbers. Let's say my velocity function is cosine of t squared. And in Mathematica, if I want to define that function, I need the underscore after the variable. And if it's cosine of t squared, I need a capital C. I need square brackets. I need an equal sign. The colon is actually optional, but I like doing it for some technical reasons I won't get into. Plot that function. What does it look like? Kind of a wild function. Gets even wilder. Actually, and also inaccurate near 15. That's not very accurate. It's oscillating faster and faster because t squared is growing faster than t does. And the graph is concave up, in fact. It's making the oscillations come faster and faster. Mathematica. What is the integral of this function? I happen to know the answer, but the answer is nothing you would ever expect. In fact, if you tried to do this integral by hand for the rest of your life, you would never succeed without knowing what I'm about to show you. You can even prove you would never succeed. Because this antiderivative that I'm about to compute cannot be written, it can be proved, it cannot be written in terms of elementary functions. What elementary functions? Finite combinations of them. They're not the kind of functions you learn in elementary school because you never learned about functions in elementary school, except for maybe tables. They are functions you learn about in pre-calc. What? Power functions, polynomial functions, rational functions, roots, square roots, exponential functions, logarithms, trig functions, inverse trig functions, and finite combinations of those things by addition, multiplication, subtraction, division, and function composition, f of g of x. Like this is a function composition right here. It can be proved this integral cannot be written in terms of functions like that. But that does not mean the integral cannot be done. It just means the answer is a function you've never heard of before. Fresnel C. Named after somebody whose last name was Fresnel. See? That actually refers to the cosine. If I change this to a sine, then the answer involves Fresnel S. Let's go back to a cosine. What is this? It's just a function you've never heard of before. That's what. A big part of what makes calculus useful is it can be used to define rigorously new functions. Evidently, if this got somebody's name attached to it, it must be important. Could I find a function who doesn't have anybody's name attached to it? Well, maybe if I come up with something crazy enough here. Cosine of t to the 10th times sine of t to the 4th. Mathematica, what's the answer? Thinking. Probably nobody has a name for it, and so Mathematica doesn't know what to write. Okay, I'm going to abort the evaluation. Probably it would come back and say, I don't know. It would come back with no output. However, these functions are honest to goodness, nice continuous differentiable functions with nice graphs, with nice areas under them. We should be able to approximate this function. In fact, if I plot this on a smaller interval, say, and add some grid lines, I should even be able to visually approximate the value of the integral. Each one of these boxes in this graph paper has an area of 0.5 times 0.5, 0.25, right? What are the units? Not meters squared. Meters, because they represent distance. Displacement, because the vertical axis is in meters per second, its velocity. The horizontal axis is in seconds. Meters per second times seconds, the seconds cancel, giving you meters. Each box represents meters. Positive change in position when the graph is above the axis, negative when it's below. There's in the ballpark of what? 4.5 or 4 boxes when t goes between 0 and 1.25 or so. So the integral from 0 to 1.25 or so should be approximately 4 times the area of each box, 0.25. 4 times 0.25 is 1. Should be close to 1. Yeah, not too far. Subtract the area here when the graph is below the axis to get an approximation for the area from 0 to, I'm typing in 0. 0 to what? About 2.2? Subtract this area. How many boxes are there? A little bit more than 2. 1 box there, almost a second box there. Add on these partial boxes. Area of each box is 0.25. 2 times 0.25 is 0.5. So maybe this number minus 0.5 or so will be this integral. So maybe 0.4 something. Yeah. That's the integral from here to here, giving you the total displacement change in position from time 0 to time 2.2. You can approximate these things, even though we can't find a formula for the function in terms of functions you're used to. That's important in this class. to realize. Next Monday, we'll talk about how to approximate these things using Riemann sums, left-hand sums, right-hand sums, trapezoid sums. Talk more about properties of integrals in chapter 6 as well.